In this video, we'll introduce the mole unit and then do some calculations that involve the mole unit. So to introduce the idea of why the mole unit is such an important unit, we need to think about this idea of counting by weighing. So we want to use a non-chemistry example to introduce this. So I want you to imagine that you owned a factory, and that factory produced small hardware pieces. Those small nuts, bolts, screws, and washers that go into a bunch of the things that we use on an ordinary basis every day in our lives. Now, as the owner of this factory, you frequently receive orders for tens of thousands of each of these pieces. Well, you want to think about how are you going to fulfill those orders. 20,000 pieces, 40,000 of a different piece, 60,000 of a different piece. That's a large number of these pieces. How are you going to fill those orders? Would you count them out? Well, maybe you wouldn't because you're the owner of the company, but would you have one of your employees count them out? How long would it take to count out all of those? It would take an incredibly long time and not be very efficient. Instead, for those small hardware pieces, those small nuts, bolts, screws, and washers, you would probably count them out by weighing them. But you might want to go through a certain procedure to do that. Imagine if you kind of weighed one of those small little bolts out, but that one that you used as a representative bolt was not actually representative of the rest of them. Anything that's mass produced like that, maybe the one you picked out was a little bit heavier or a little bit lighter than what the rest of those bolts would be. Well, if that's the case, you would run into two problems. You would either not give the customer enough by weighing them out, or you might give them too much, which kind of hurts your profitability. So instead, what you might do is you might randomly pick out 100 of those different bolts and weigh them. And in that way, if you had one that was a little bit lighter or a little bit heavier, it really wouldn't throw off the count by very much. So you might do this procedure for little bitty things such as those little bitty nuts, bolts, screws, washers in order to efficiently count out large numbers of them. Well, if you have to do this procedure for small hardware pieces like that, you would definitely need to use this idea of counting by weighing for things that are even smaller, for atoms and molecules. We've already talked about how small atoms and molecules are. If you need to do that for things you can actually physically manipulate and see, like those nuts, bolts, screws, and washers, you are definitely going to need to do that for things that are much, 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 much smaller. So we're going to use this counting by weighing, not just for these little hardware pieces, but instead to start relating these to actual chemical principles for dealing with quantitative work for atoms and molecules. So we want to introduce the mole unit. So when we're thinking about the mole unit, there's a couple of definitions for a mole. The first definition of a mole is that the mole is just a counting number. It just happens to be a very, very large counting number. One mole is 6.02 times 10 to the 23rd. Now, if we're not that familiar with scientific notation, that would be like moving the decimal place 23 places to the right. It's an incredibly large number. And the reason why it's such an incredibly large number is because the things you're counting with moles, atoms, molecules, are so incredibly small. But the mole is still a counting number. And if we really think about it, the mole acting as a counting number is really no different than other counting numbers we're dealing with. When we say a dozen, we mean 12. It doesn't matter what that dozen is of. We can talk about a dozen eggs, a dozen donuts, a dozen pencils. A dozen's always 12. A mole is always 6.02 times 10 to the 23rd in terms of it acting as a counting number. But we're going to have trouble using that as a real counting number. Because the number is so large, it has limited practical uses. It's a very cumbersome number to deal with. Because it's such a cumbersome number to deal with as a counting number, we want to think about, is there another way we can deal with a mole? And there is. So besides the mole being a counting number, it also has a counting by weighing definition. Remember, we just talked about how we could use this idea of counting by weighing for those small little hardware pieces, those nuts, bolts, screws, and washers. Well, we're going to see that the mole has a counting by weighing definition as well. And this counting by weighing definition for a mole is just related to the AMUs for the elements. Now, if you kind of go back to think, I'm showing carbon here on the slide. We talked about that 12.011, that average mass for carbon being in AMUs, those atomic mass units, those kind of made up units that get us down to that small scale. But we can do better than AMUs for this. So that 12.01 AMU average mass now also can be used as a counting by weighing definition. And instead of that being AMUs, now that's going to relate to our counting by weighing. And here's how that relates. Every time you see an average mass number for an element, that's the mass it takes for you to get 1 mole of that element. So when you see 12.01 for carbon, what that really means is that there are 12.01 grams of carbon for every mole of carbon. That relationship is called the molar mass. How much mass does it take to equal 1 mole of that substance? We can weigh out 12.01 grams very, very easily. However, we can never really count up to 6.02 times 10 to the 23rd. That makes this counting by weighing much more practical and much more useful. And it doesn't just work for carbon, it also works for all of the other elements as well. So every element you see on the periodic table, that average mass, those AMUs, that's telling you how many grams of that substance it takes to give you 1 mole of that substance. So if you would look at phosphorus on the periodic table, 1 mole of phosphorus, 30.97 grams of phosphorus. If you look at calcium on the periodic table, 40.08 grams of calcium, 1 mole of calcium. That average mass that you see for each element is how many grams of that element it will take to give you 1 mole of that element. So if you kind of go back and think about that, the periodic table now for us becomes one gigantic unit conversion chart that we can use, and we always have access to it. Any element we want to deal with. If we're interested in copper, if I circle copper here, that's 63.55. What does that mean? That means for copper, 63.55 grams of copper is 1 mole of copper. Any element we're looking at, if I circle bromine here over to the right, 79.90. What that means now for us is 79.90 grams of bromine is 1 mole of bromine. And any element we look at, if I circle potassium here on the left-hand side of the periodic table, 39.10 grams of potassium equals 1 mole of potassium. And now the periodic table does more than just organize elements into groups with similar chemical properties. It now has an even more useful role. Now, the periodic table is now a gigantic unit conversion chart. And it's a gigantic unit conversion chart that you always have access to. You don't really have to memorize any of the weights on there. You always have access to it. You just have to recognize that every time you look at one of those average masses, What that's telling you is that many grams equaling 1 mole. We're going to do some example problems with that. So before we get into some example problems, you saw that we had two definitions of a mole. So we had mole as a counting number, 6.023 times 6.02 times 10 to the 23rd atoms of carbon is 1 mole of carbon. That's using that counting number definition. Well, we also saw that counting by weighing definition from the periodic table, 12.01 grams of carbon. So mole has two definitions. So in this kind of triangle or pyramid-like structure that I have, I put moles at the top. And we see that moles have two different definitions. One is that counting number definition using 6.02 times 10 to the 23rd. That's sometimes called Avogadro's number. The other definition, kind of on the right-hand side, moles will relate to grams. How are we getting that information? Using the average masses that we're seeing on the periodic table. So for what we're working on, we're never going to use that counting number definition, that 6.02 times 10 to the 23rd. That has no practical, useful purposes for us. We are always going to be using the other definition, the relationship between grams and moles using the periodic table and those average masses that you're getting from that periodic table. I want to do some examples of how to use that information. And here's our first real chemistry problems. We've done some unit conversion problems previously in the first unit of the course. Well, now we're using that technique to solve more chemistry specific problems. So here's our example. Diamonds are made up of pure carbon. If a diamond has a mass of 315 milligrams, how many moles of carbon are present in that diamond? Now, at first glance, this may look like a chemistry word problem. And it is kind of a chemistry word problem, but we want to treat this the same way we would any other unit conversion problem, because that's what it really is. We're going to use dimensional analysis in order to solve this. How are we going to do this using dimensional analysis? Well, same way we've done every other dimensional analysis problem. It's going to start with a two-row table. What are we going to put in first? Well, we're going to put in our starting information, 315 milligrams of carbon. What do we want to achieve at the end of this? If you want, you could still write out your goal at the end. That's okay. We didn't kind of show it in this one, but you could still write out your goal in the last box if you wanted. You could still get your moles of carbon in there. So now, how do we go about this? Well, we just saw how we can now have a relationship between moles and grams by using the periodic table. But before we can use that relationship, we would have to first get our quantity in grams. Well, we're in milligrams. Can we go from milligrams to grams? Yes, this is something we've done a lot of already. What's the relationship between grams and milligrams? Well, 1,000 milligrams in every gram. Where would we put the milligrams? Well, the milligrams of carbon will go in the denominator. That way they will cancel with the milligrams that we already have in the numerator. We'll put the grams in that numerator. So now we can see that our milligrams of carbon are going to cancel. This is a step that we've already done before. You've done this step many, many times in that very beginning of the course when we were dealing with metric. It still applies here. Now that we're grams of carbon, how can we get into moles? Well, this is the new step. The grams and milligrams step, that was the old step. Now it's a new step. Well, how can we get from grams to moles? Well, you would look up that conversion on the periodic table. When you look up carbon on the periodic table and you see carbon is at 12.01, what does that 12.01 mean? Well, we kind of already talked about it. That 12.01 means that there are 12.01 grams of carbon in a mole of carbon. That's that relationship. That's what the 12.01 on the periodic table means. Now we can use this just like we would any other unit conversion factor. What unit do we want to get away from? We want to get away from grams. So being I have grams of carbon in the numerator, I want to put my grams of carbon in the denominator, so those are going to cancel. I want to be left with moles of carbon, so that's going to go in the numerator. And we're still going to cancel just like we've done before. Grams of carbon in the numerator will cancel with grams of carbon in the denominator. The unit that we're left with, moles of carbon, is the unit we want to be left with. So that means we have this set up properly. We just have to do our final calculation, and the calculation works the same way as all of our other calculations have worked. Anything in the numerator is a multiplication. Anything in the denominator is a division. Well, now that we have that, what do we have in the numerator? 315 divided by 1,000 divided by 12.01. Calculation works the same way in any dimensional analysis problem. Numerators are multiplication, denominators are division. So we would key this in as 315 divided by 1,000 divided by 12.01. And when you do that, you would get your final answer, 0.026 moles of carbon. So in order to do this step, there's really only one new thing. The new thing is the gram to mole relationship, and you're getting that from the periodic table. Everything else, kind of what I'm pointing at in blue right now, everything else, you've done that already. You've been there, you've done that, you've done those conversions. So the new step is bringing in these gram to mole relationships. If we look at another problem here, in this problem, you're starting with 1.47 moles of iron. This one's going to be essentially the opposite of the problem we just did. And we want to figure out how many ounces of iron is this. And we were given some useful conversions. 16 ounces in a pound, 2.2 pounds in a kilogram. Well, this is a dimensional analysis problem. This is why we learned the technique earlier in the course, so we could apply it to actual chemistry problems now that we're starting to get a little bit more into chemistry-specific content and chemistry-specific calculations. So how will we start it? You're going to draw a two-row table. What information are you starting with? 1.47 moles of iron. At the end, what do we want to achieve? Ounces. Well, for moles, we know there's only one thing we can do with moles. The only thing we can do with moles that we really know about is to relate it back and forth with grams. And how do we do that? We do that from the periodic table. So when we look at iron on the periodic table, we find iron on the periodic table, and it says 55.85. What does that 55.85 mean? Well, that means that there are 55.85 grams of iron in 1 mole of iron. We're just pulling that right from the periodic table. That's what the 55.85 mean. And now, using the same techniques we've always done using dimensional analysis, we want units to cancel. Well, that means the mole part of that equality will go in the denominator in order to cancel with the moles that are starting in the numerator, and our grams will go in the numerator. That will allow the moles of iron to cancel. Now that we're at grams of iron, now we're just going from grams to ounces. This has really changed. We took care of all the new information right away in this first step. Everything else, going from grams to ounces, now we're just going back to those conversions that we did in the first unit. It's really now a kind of first unit problem, not a second unit problem. We took care of the new information with the grams and the moles. Now it's just going grams to ounces. Well, that's English to metric. So whenever you have an English to metric change that you want to make, you want to find that translator equality. The translator equality would be 2.2 pounds equals 1 kilogram. So we know we have to use that. Well, right now I'm in grams. Before I can use that translator equality, I would have to go to kilograms. Well, we know how to go from grams to kilograms. That's something we have done a lot of already. We're just doing it again. I want grams to cancel, so my grams of iron will go in the denominator in order to cancel with the grams in the numerator, leaving the kilograms of iron in the numerator. So we're going to be able to cancel off our grams of iron, numerator and denominator. Now we're at kilograms of iron. Well, now that we're at kilograms of iron, we can use that key translator equality that we identified earlier. 2.2 pounds, 1 kilogram. We're going to use that. We want our kilograms to go away, so our kilograms will go in the denominator to cancel with the kilograms we started with in the numerator, and we'll put our pounds in the numerator. Our kilograms of iron will cancel, leaving us with our pounds of iron. At this stage, we're in English units, which is what we wanted, but we're not in the right English units yet. We need to be in ounces. But we have a way of going between ounces and pounds. We have that conversion, 16 ounces, 1 pound. That was provided for us. We just have to use it. We want to go away from pounds, so we have pounds in the numerator, so our pounds of iron need to go in the denominator such that they will cancel. That'll place our ounces of iron, so our ounces of iron will then go into the numerator. Our pounds of iron will cancel, numerator and denominator, those will cancel. Everything has canceled except the unit that we want, which is the ounces of iron. So we have this set up properly. At this stage, we're just doing the final calculation. The calculation works the same way as all of the other calculations have worked. Everything in the numerator is a multiplication, and everything in the denominator is a division. So the way you would key this into your calculator, you'd have your numerator 1.47 times 55.85 times 2.2 times 16, and then divided by 1,000. So 1.47 times 55.85 times 2.2 times 16 divided by 1,000. And when you do that, your final answer will be 2.89 ounces of iron. When you look at these steps, there's only one new step that you should really be seeing, and that was the first step, the one pointing to in purple, grams and moles. How many grams per 1 mole? Well, you're getting that from the periodic table. All of the other steps, kind of putting them red X's above that, all of these other steps, kilograms and grams, been there, done that. We're good on that. Pounds and kilograms, been there, done that. That's old news. Ounces and pounds, been there, done that. So there's only one new thing to be able to successfully do these problems, and that's doing that gram to mole relationship, and you're just grabbing that information from the periodic table. Those masses on the periodic table are telling you how many grams per 1 mole. We're now just using that and incorporating that in with all of the other unit conversions you already know how to do. So the two examples we just did worked for elements. Well, most of the matter you deal with are not things in their elemental form. We need to be able to deal with molecules and compounds as well. So everything we just did for atoms is also going to work for molecules and compounds. The only thing we have to do is we need to treat our molecule or our compound as just a total collection of atoms or ions. When we think about it in that way, the total for a molecule or compound will just equal the sum of all of the parts that make up that molecule or compound. So we're going to do some examples dealing with this next. So first, just some examples of counting things up. So our first example is we're going to try to figure out the molar mass of N2Br4. Well, N2Br4 is a molecule. If we want to figure out what's going on for the total of N2Br4, we just have to sum together all of the parts. And we kind of already know how many of each part is present from when we did the nomenclature. We know we have 2 nitrogens. Well, if we have 2 nitrogens, we look up nitrogen on the periodic table. Nitrogen on the periodic table is 14.01. So we get 2 nitrogens at 14.01 each. Then we have 4 bromines. So we find bromine on the periodic table. Bromine on the periodic table has a mass of 79.90, and we have 4 of them. So we get those in. Then to figure out what's going on with the total, we just combine. We would add together all of these parts. We just listed all the parts. We're going to add those together to determine what that total is. And when you add all of those parts together, you will get that total. And that total for N2Br4 is 347.62. That's your sum total from combining everything together with that. So what that means is that the molar mass of N2Br4 is 347.62 grams per mole. Remember what that means. That molar mass means that many grams per 1 mole. So if you had to use that as a equality, what that really means is 347.62 grams of N2Br4 is 1 mole of N2Br4. And then you would use that equality just like you did for the molar masses for single elements. Now you're just doing it for a compound. You totaled up all of the individual pieces to figure out what's going on for the total. Now we can do another example on the right-hand side for figuring out the molar mass of Mn2SO4 Here you're seeing that polyatomic ion. You're seeing the parentheses. So remember, we dealt with that in the nomenclature. Again, you're just summing up all the parts. So you look at the manganese. How many manganeses do we have? Well, when you look at the manganese, you're going to see we have 2 manganese. So each manganese is at 54.94 when we look it up on the periodic table. We have 2 of them, so we can total together all the manganeses. Next, we'd look at the sulfur. Sulfur on the periodic table is 32.07. How many sulfurs do we have? Well, remember what the parentheses tell us. The parentheses tell us groupings. So in each group, inside the parentheses, we have 1 sulfur. How many of that group do we have? Well, that's what the subscript 5 outside the parentheses are telling us. We have 1 sulfur in the parentheses, 1 sulfur per group, but 5 of those groups, that would mean 5 sulfurs. Well, 32.07 for each sulfur, we have 5 of them. We would get our total from our sulfur at 160.35. We do the same thing for our oxygen. We'd find oxygen on the periodic table. Well, oxygen on the periodic table has an average mass of 16. How many oxygens do we have? Well, if we look at oxygen, there are 4 oxygens per group for SO4. So 4 oxygens per group. How many groups do we have? We have 5 of those groups. So 4 per group and 5 groups. 4 times 5 gives us 20. We would have 20 oxygens total in this molecule. So oxygen comes in at 16, and we have 20 of them. That would give us an oxygen total of 320. And again, just like before, we would take all of our parts and add up all of our parts together. So the total for the entire compound for Mn2SO45 from adding together all of those individual parts would be 590.34. So what that means is that the molar mass of Mn2SO45 is 590.34 grams per mole. 590.34 grams of that substance is going to equal 1 mole of that substance. So anytime you have a molecule or a compound, you just have to add up all the individual pieces to figure out what's going on with the total. We kind of put both those pieces together in an example. Dry ice is sometimes used in shipping perishable foods to keep the item cold or frozen. Dry ice is actually not ice at all. It's actually just solid CO2. It's solid carbon dioxide. We want to determine how many moles of CO2 are present in a 1.5 pound brick of dry ice. And we'd be given some useful information, 2.2 pounds in 1 kilogram. Now again, even though this looks like a chemistry word problem, we're treating that not as a chemistry word problem. We are treating this as a dimensional analysis problem. Being it's a dimensional analysis problem, what do we want to do? We want to draw a 2-row table. So draw your 2-row table. Get your starting information in there. Pounds of CO2. Well, what do we want to achieve at the end? Again, not shown on the slide, but we could write it in if you wanted to. What's your goal at the end? Your goal at the end is moles of CO2. So you can get that in there if you want still. So we only know one way to figure out moles, and the way to figure out moles is from grams. So we got to get the pounds to grams first. Well, pounds to grams, how's that going to work? Works the same way pounds to grams worked before. This is essentially just some unit 1 type steps. I'm in pounds, which is English, so I want to get to metric because I know grams is metric, so I got to start getting to metric. Do I have a way to get from English to metric? I do. It's provided for us. 2.2 pounds is 1 kilogram, so I can use that right away. I want to place the pounds in the denominator because I started with pounds in the numerator. Then I'm going to put the kilograms of the CO2 in the numerator. This will allow us to cancel off our pounds of CO2. So now we're currently at kilograms of CO2. Well, in order to get to moles, moles come from grams. So I would need to do kilogram to gram conversion, changing my metric unit. That's not a problem. That's something we've done before. Well, we've done it before. How many grams in a kilogram? Well, there's 1,000 grams in a kilogram. Where do we want to put the kilograms? Well, we want to move away from the kilograms. We started with kilograms in the numerator, so kilograms of CO2 will go in the denominator, so they will cancel. Our grams of CO2 will be placed in the numerator. We can see that our kilograms of CO2 are set up to be canceled. Kilograms in the numerator, kilograms in the denominator will be canceled. Now we're at grams of CO2. Now we're looking at getting to moles of CO2. How are we going from grams to moles? Well, that's the molar mass in the periodic table. Here we have CO2. We have a molecule, so we have to look at the individual pieces. So this is done on the left-hand side of the slide. We look at CO2. What do we have? We have 1 carbon. Carbon comes in at 12.01. We have 2 oxygens. Each oxygen comes in at 16. So what would we do? We would total all of these pieces together. And when you add up those pieces together, you'll get the total for CO2, which is 44.01. The molar mass of CO2 is 44.01 grams per mole. So remember what that means. That's going to mean that when we're talking about CO2, we're going to have 44.01 0.01 grams of CO2 equaling 1 mole of CO2. That's what that molar mass means. How many grams does it take to give you that 1 mole? Now we're just going to use it as a conversion factor. I have grams of CO2 in the numerator already, so that means I need to place my grams of CO2 in the denominator, placing my moles of CO2 in the numerator. You can see we have grams of CO2 set up to be canceled again. So we're ready to cancel that. Grams of CO2 will cancel. Unit we have left, moles of CO2, is the unit we want. So this is set up properly again. Now we just have to calculate things out the same way we've done every other calculation. Every value in the numerator is a multiplication. Every value in the denominator is a division. So in order to key this into your calculator, 1.5 times 1,000 divided by 2.2 divided by 44.01. And when you do that, you should get a final answer of 15.5 moles of CO2. If we go back and look at the setup for this, again, you're going to notice that there's only one new step. The only new step is this gram to mole conversion coming from information on the periodic table. All of the other steps, again, kind of shown with the red X's above, well, kilograms and pounds, we've been there, done that a lot of times. Grams and kilograms, been there, done that. In these problems, in order to do these problems, all you have to do is incorporate that new gram to mole step into what you're already able to do for unit conversions and dimensional analysis. We want to look at one more problem, and in this problem, we're asked how many moles are present in 436 milligrams of calcium nitrate. So again, this is a dimensional analysis problem. Set up a 2-row table for yourself. Put your starting information in there, just like always. 436 milligrams of calcium nitrate. What do we want at the end? At the end, we want moles of calcium nitrate. So we know that the only way to really get at moles is if we have grams. So our first step is going to be a milligrams to grams conversion. Again, just using information that we've previously done. We know that 1,000 milligrams equals a gram. So 1,000 milligrams of calcium nitrate will be 1 gram of calcium nitrate. I'm starting with milligrams of calcium nitrate in the numerator. That means the milligrams of calcium nitrate need to be placed in the denominator. That would place the grams of calcium nitrate in the numerator. That sets it up such that we can cancel off our milligrams of calcium nitrate. Milligrams of calcium nitrate in the numerator will cancel with milligrams of calcium nitrate in the denominator. What that's going to leave us with is grams. Well, we know that once we're at grams, we can go to moles by using the information on the periodic table. We just need to figure out the total molar mass for that compound. We can do that on the side here in the bottom left. So how many calciums do we have in the molecule? We have 1 calcium. We did a little bit of rounding. We've been working hard this video, so I just rounded that to 40 for this example. Now, how many nitrogens do we have? Well, each nitrogen comes in at 14.01, but how many of them do we have? Well, if we look at the molecule up here in the upper right, we see we have 1 nitrogen per group. That's the information you're seeing inside the parentheses, the grouping of that. And then you see that outside the parentheses, how many of those groups do we have? We have 2. So we have 1 nitrogen per group, but we have 2 groups. So 1 times 2 is 2. So we're going to get our total nitrogens coming in at 28.02, 14.01 each, and we have 2 of them. Next, we would be looking at the oxygen. So oxygen on the periodic table has that average mass of 16. How many oxygens do we have? Well, if we go back to looking at our molecule, inside the parentheses, we have 3 oxygens. That means there's 3 oxygens per group. Subscript outside the parentheses tells us how many of those groups we have. Well, 3 oxygens per group, and we have 2 groups. So that would be 3 times 2 for 6. We have 6 oxygens, so for oxygen, 16 each times 6, that would give us a total of 960. Or sorry, not 960, 96. We would have a total of 96. So now we would just take our individual pieces. Those are our individual pieces. 40 for calcium, 28 total for the nitrogen, 96 for the oxygen. We would add up all those pieces together. We would get the grand total of 164.02. So calcium nitrate's molar mass is highlighted in green, 164.02 grams per mole. Remember what that means. That means that when we're talking about calcium nitrate, CaNO3 that means when we have 164.02 grams, 164.02 grams of our calcium nitrate, that is 1 mole of our calcium nitrate. Remember to sum up all the individual pieces to give yourself that total. Now we just have to use that as a conversion factor. I have grams of calcium nitrate in the numerator. That means I want to put the grams of calcium nitrate in the denominator such that they will cancel, and that will leave us with moles of calcium nitrate in the numerator. We can go ahead and cancel our units now. Grams of calcium nitrate in the numerator will cancel with grams of calcium nitrate in that denominator. What are we left with? Well, we're left with moles of calcium nitrate. That's exactly what we want to be left with. So this is set up properly. How do we deal with this final calculation? Well, same thing as all the other calculations. Anything in the numerator is a multiplication. Anything in the denominator is a division. So how do we key this in? 436 divided by 1,000 divided by 164.02. So that would be 436 divided by 1,000 divided by 164.02. And when you go ahead and you do that, you should get a final answer of 0.00266 moles of the calcium nitrate. So again, the only new step in this, so our new step that we're looking at is just the gram to mole piece. That's the only new thing for all of these calculations is the gram to mole step. And you're getting that information directly from the periodic table. All of the other steps, whether they be metric to metric steps, English to English steps, or English to metric steps, here we saw a metric to metric step, are all things we've done before. You're very familiar with those already. So if you're comfortable with dimensional analysis and unit conversions and you know your metric prefixes, then you're going to have a pretty straightforward time dealing with this new content because it's only one new thing that you're adding on to that. And you don't have to memorize anything for that. It's just pulling that gram per mole information right off from the periodic table.